So along with using the concept that log functions and exponential functions are inverses of each other, graphing one and reflecting across the line y equals x, we can also do something like an example 5, page 194. It says we're going to sketch a graph of the common log function f of x is equal to log, we know it's base 10, but they wrote it in there, log base 10x by hand. And they're going to start with a table, so understanding a lot about this already, you guys in exponents, you understand how those work. We have this simple fact. How do we get 10 to become 1 over 100? How do we turn 10 into 1 over 100? Well, 10 squared is 100. 1 over 100 indicates that we have a negative exponent, and a negative 2 indicates 10 squared is in our denominator. And so it follows that when 10 to what power is 1/100th, 10 to the negative 2 is 1/100th. And they go through the table. How do we get 10 to become 1/10th? Raise it to the first power, but a negative power, putting that base, that 10, in the denominator. How do we get 10? 10 to what power is what we're asking. 10 to what power now is 1? Well, that's a good one. Anything to this power is 1. We understand that to be 0. So we're accumulating, or we're piling up these ordered pairs that we can now plot in order to plot the basic function log of x. These are the easy ones. 10 to the what power is 10? 10 to what power is 10? 10 to the first power is 10. And then, of course, it becomes not so obvious. 10 to what power is 2? The next one. Well, 10 to what power is 2? Well, we know this has to be something less than 1. And we're going to use our calculators for that, remembering back to one of the examples where we just put log 10 and put in our power. So problem 45 kind of sends us into a tailspin here. It hasn't covered any of this, but I'm going to go over this with you. It asks to find the domain and vertical asymptote and x-intercept of the log function and sketch the graph by hand. Well, we know how to sketch the graph, but I want you to look at this function log base 2 x plus 2 is equal to y. What we're saying is 2 to some power is x plus 2. 2 to some power. Well, 2 to any power, I want you to think about the restrictions on that. Can we ever get a negative value by taking 2 to a power? A negative power just gives us a fraction, getting smaller and smaller as x approaches negative infinity. And a positive x value, 2 to some power, gives us larger and larger numbers, doubling every time. So we understand this restriction on this expression, 2 to some power, x plus 2 has to be bigger than 0. It can never be less than 0. It can never be negative. So when we talk about restrictions, we're talking about domain and we're talking about vertical asymptotes. So we see from this first part of the problem that x is greater than negative 2. Domain is all values greater than negative 2, and at negative 2 we are undefined and we have a vertical asymptote. Well, the next part of the problem is asking for a y-intercept. We just found the domain, the vertical asymptote, and we need an x-intercept, excuse me. So the domain, all real numbers greater than -2, vertical asymptote equals -2. And in order to find an x-intercept, we need to set the y value equal to 0. That will allow us to find our x-intercept. So log base 2 of x plus 2 equals 0. This is saying to us 2 to the 0 equals x plus 2. 2 to the 0 is simply 1. 1 equals x plus 2. X equals -1 is our x-intercept at -1, 0. Found domain, vertical asymptote, and our x-intercept. So on page 195, a library of parent functions again, we're looking at the parent log function. F of x is equal to log base A x. We have seen transformation properties. I want you to look quickly at example 6. It says we have g of x equaling log base 10. We don't have to write it unless it's different from that. Minus 1. This is the parent function f of x minus 1. And we know that that looks just like x minus h. So we can assume, we can make a very strong assumption that this is moving our graph horizontally to the right one place. So we've taken the parent function and shifted it right 1. If you look at the second one, it says h of x. H of x is equal to 2 plus log 10. We don't have to write the 10, it's understood. X. This is the same as 2 plus h of x. And we can see and remember that looks a lot like h of x plus k, a vertical shift. So we know that this graph is shifting upward 2 units. I'd invite you to look over page 196, the natural log function. The natural log, base e. The box at the top of 196 gives us some basic characteristics which are identical to the log base 10, and we can see that they are closely related. Example 7, evaluating natural log functions in exactly the same way we evaluated base 10 logs. If f of x is equal to log x, for x equals 2, we simply, on our calculator, log 2 and enter. And what that's saying is e to what power is 2? Well, we can make a really good guess. E is 2.718. So e to what power is less than its actual self? This needs to be a fraction, this value. Our power, our exponent, needs to be less than 1 in order to give us that value less than 2. If we look at the properties of natural logs at the bottom of page 196, we notice the same exact properties. Log 1 equals 0. This is saying log base e, e to the 0 is 1. You'll notice all the rest are exactly like the base 10 logs. I'd like you to look at 3. It says log e to the x equals x. Again, we're saying this base e, e to the x equals e to the x. It's known as the inverse property. Along with that, e to the log x, log x as an exponent, equals x. What's happening here is e to the log base e up here cancels, and we're left with x, x equaling x. Turning to the top of 197, using these properties, the log, the way to think about this, the log 1 over e is saying e to what power is 1 over e. Well, anytime e ends up in that denominator, I don't see any other power. I see a 1 or understand a 1. We know that's the negative 1 power. Negative 1 placing that base in the denominator. Finding domain and range, or excuse me, finding the domains of log functions. Looking at example 9, it says find the domain of each function. First one being f of x equal to, this is the one we should have had earlier, log x minus 2. It says because the log, natural log, this is just like our base 10 problem that we did in problem 45, is defined only when x minus 2 is greater than 0. We understand the domain is all values greater than 2. And we would write that greater than 2, not equal to 2. It's not defined at 2 to positive infinity. Go ahead and read through example 9, parts B and C, and then try problem 89, and we'll meet right back here. So very similar to problem 45 that we worked out, this is just a natural log. We understand that e to any power needs to be greater than 0. So any power being, what is that power we're going to be taking? X minus 1 needs to be greater than 0. X needs to be greater than 1. So the domain we can write as 1 to positive infinity. It's lovely. And the vertical asymptote, of course, is undefined at 1. X cannot equal 1. Vertical asymptote exists at x equals 1. Again, we ask ourselves, for an x-intercept, that means we allow y to be 0. So we're coming right from this function. F of x is 0, log x minus 1. Now we're saying e to the 0 is equal to x minus 1. We know e to the 0 to just be 1. Where is 1 equal to x minus 1? We know x, adding 1 to both sides, x is equal to 2. And so we have an x-intercept at 2, 0. So we can start to use these points and these characteristics of our graph to start to sketch.